Say hi. Okay, so for today's class, we're going to do a little Atwood machine problem for review. So let me show you what the setup is. Okay, I don't know how you can see it, but we have a car sitting here, and it's going to accelerate forward, and we want to figure out what the acceleration of the car is and the tension and the strength. So other students are doing this. Here is your information. So once you copy this information down, I want you to pause it before we show the actual results. So the car's mass is 0.85 kilograms. The hanging mass is 0.15 kilograms. You want to figure out what's the rate it's going to accelerate and what the tension is, and we're going to test it out with the Bluetooth. Okay, so let's get ready to test. I'm going to control things back here. You're going to watch on the screen there because that's what I want to try to do is share. So let's see. I want to share my desktop. This is going to take me a minute. What do you mean it switched? You can see my screen back here now, I hope, right? Yeah, that's what I want. Okay, so what I have here is the force sensor that's going to measure this. And then the really nice thing is I can switch it over to acceleration. So all I got to do is make sure it's reading the car. So for those of you doing this at home, you should pause here, work out your calculations before you look at the results. Okay, so first question before we do this. What should we expect about the tension when it's being held right here? All right, I hold this before I release it. What do we expect to be the tension?
Like our answer over there?
No, the answer over there is when I release it. So I'm asking when I'm holding it, is the tension the same or is it different? And if it's different, what value should we expect it to be? Do you want to huddle together and talk about that?
Be the same, right? There's still the force of gravity pulling down on that. So tension has to be close.
Look at your solution. Does your solution support that? Your equation, not your numerical. Look at the equation. Is there anything different about this situation that shows up in your equation?
Yeah.
What?
Acceleration.
Okay, what about it?
It would be 0 right now.
That's true.
So since you multiply the acceleration by the mass, it would be like that's you find the tension.
I'm trying to find tension now. So what they're saying is if your acceleration is 0, then your MA is 0. So what does that mean about the tension on a string? I see what you're doing. I see the problem. You got T equals this mass times A, and this A is 0. There's a problem with that, right? Either the tension is 0. Well, if you were to draw a force diagram now, would anything be different?
Oh, that right there. Yeah, because you're resisting.
I've added a force here, have I not? I applied force to my hand. Which way is it? And tension is this way here. So what do you know about those two? How do they compare? They're opposite. How their values compare? Magnitudes. They're equal. Okay, well, that means they're not 0. So how would you figure out the tension? I don't need to. I could, but I don't need to.
Find how much force is acting on.
I don't know, can you?
Oh, yeah. Yes, you can.
Oh, really? Wow.
Because
Well, someone help Ben out. What? Say that again. Whoa, stop there. Are the tensions equal?
yes,
How do you know?
very well.
They're law, action, reaction, right? So yes, the tensions have to be equal. Okay, continue.
So if they're equal in that way, it's going down, that's the same way it's going barely back.
So in other words, the tension is equal to what? Mg, which M? What's that M? How much? What's 0.15 times 10? So we expect the tension to be roughly 1.5. And when I let it go, what is the tension? What did you predict? 1.2 or so. Okay, let's test it out. All right, I'm going to turn on the force sensor. You're going to be able to best see it up on the screen on the smart board. Okay, can you see it? What's it reading? All right, exactly as we expected it. Okay, so now I'm going to release it. Actually, let me pull it back a little bit so it can go for longer so we can get more data. Okay, let it settle. All right, so let's stop it. And you can see where it's flattish. All right, let's see if we can expand that a little bit because it's hard to read. I did not want to do that. I hate this thing. Hold on. Hold on. Back to where we had it before. There we go. Can you read it now? Maybe get a little better precision. And what is it centered on? 1.2. Wait, we got to check the acceleration. Watch this magic. I can just click this button and I click acceleration. And then it gives us that. We're looking up here. What is it reading?
5.
What did you predict?
1.47.
Is that close enough for you?
Yeah.
Are you sure?
Yeah.
You guys did that very easily. That's good. I hope all four of you feel like you can do that easily. And it wasn't like you memorized things, right? What did you do to get this? It's not like you memorized an equation. Did you memorize an equation for acceleration? What did you do to arrive at this?
Look at the notes.
Wait, wow.
We have the equation now.
The T oh, damn. What if we didn't have your notes? Oh, I thought you were going to tell me, oh, we drew a force diagram, we expressed F net, we did this process. I was hoping this process was much easier for you now. Oh, boy.
I thought it was a little too easy.
Yeah, I thought so. Okay, maybe we need to do another one. All right, so no notes. Oh, don't make it sound like this is so painful. You're missing a point. This is help you get ready. All right, same problem. Now, I'm going to shift 0.2 kilograms over to the hanging. So I'm going to have 0.35 here. And 0.65 here. 0.65, 0.35. Notice I haven't changed the mass. It's like that experimental problem in the test, but I have changed the, I've changed FNet. I've changed the accelerated force. All right, same question. What's the acceleration? And what's the tension?
We're drawing an FPD for as it's accelerating, right?
Yep, it's accelerating. All right, I'm going to stop the recording.